let's now talk about the coupling of the nonlinear transform with the optimal fat separator. Now, first, let's look at the nonlinear transform with our old technology, just a plain old-fashioned linear model, and and our algorithm that we will use in the z-space is the pseudo-inverse algorithm. So we'll use linear regression for classification. Okay, so now what's our z-space? We're doing the third order polynomial, so phi sub 3. Okay, and then the pseudo-inverse linear regression for classification, and we get our classifier in the z-space in the third order polynomial. Okay, and then we see what that decision boundary looks like in our X space, and it's this, it separates the data as the nonlinear transform is designed to do. Okay, but it doesn't take much to convince you that there's a little bit of overfitting going on here, because you have a lot of parameters to play with in the third order polynomial feature space. Okay. And so we've overfit the data. Now, let's see what happens if I use the same z-space, and this is very important. I'm using exactly the same z-space. So I'm going to use the third order feature transform, but instead of the pseudo-inverse algorithm, let me get the fattest separator, the fattest hyperplane that separates in this third order feature space, okay, and then see what the corresponding decision boundary is in my original, two-dimensional features. Okay. And there you go. Wow! Okay, look. Considerably less overfitting, and it more or less reproduces the target function. And I'm showing in sort of yellow the thickness of the separator. Okay, and I've boxed the support vectors, and you will observe that in this third order feature space, you have a lot of parameters. You have a lot of degrees of freedom. All the parameters for this general third order polynomial. But effectively, what determines the separator is just these 6 support vectors. So even though you have a lot of flexibility, a lot of degrees of freedom, the separator is effectively determined by just a small number of support vectors. Okay, and you will observe another interesting thing is that we saw when we discussed the linear fattest hyperplane, the thickness of the hyperplane was the same on both sides and uniform. Well, that thickness is the same and uniform in the z space. In the actual x space, you see that the thickness of this separator varies. Okay. But the main point here is the theory in action. Even though you have the flexibility of the third order polynomial, once you put this constraint that you're going for the fattest separator, effectively it lowers the number of degrees of freedom. The cross-validation error is related to the number of support vectors, not the number of degrees of freedom, the dimension. Now, just for comparison, I also did the transform to the second order polynomial space and used the support vector machine, the optimal fat hyperplane, and you see it's beautiful. This is basically the target function, more or less. Okay, and now we have 1, 2, 3, 4, 5 support vectors, and we have a nice yellow, fat separator. Okay? And what you will observe is that in going from the second order polynomial to the third order polynomial, you've almost doubled the dimension of the space, but the number of support vectors just went from 5 to 6, nowhere close to double. Okay? And this gives us a lot of hope that we can go to high dimensions, okay, and still get good performance like this third order polynomial versus the second order polynomial. And what's saving us? What's saving us is the robustness of the fattest separator, okay, which effectively reduces the number of degrees of freedom to the number of support vectors which control the boundary, as opposed to the number of degrees of freedom, which could result in this very complicated separator if unregularized. So the support vector machine, linear model in the nonlinear transform space, in some sense automatically maximally regularized. It allows us to use the complex decision boundary without suffering the penalty of all the degrees of freedom. It constrains the model significantly. Regularization at work, but in this case, automatic regularization at work. And what controls the performance is the number of support vectors. So this leads us to an interesting possibility. Can we go to even higher dimensions? Can we go way beyond the third order polynomial? Can we go, for example, to infinitely many dimensions? Wow! Imagine being able to perform, a nonlinear transform to infinitely many dimensions and then separate. Then we can separate anything. Right? But then should we be overfitting? Well, if the number of support vectors is kept under control, or if you can do this with very large margin, then you have control, large margin, because that's the DVC, is the bound is the bounded data, the tightness for the bound of the data divided by the margin squared. Right? If you can control that, or you can control the number of support vectors, then we can control E out, okay, and benefit from infinitely many dimensions. Wow! Okay. So separate the data with huge margin in large large dimension. Okay, but then there's the issue of, does this really work? So will we be able to control the number of support vectors? So does it really work? And what are we talking about? Infinitely many dimensions? How do you go to infinitely many dimensions? What kind of a feature transform transforms us into an infinitely large, infinitely dimensional Z space? We're not going to be able to do that. How can we do that efficiently? We'll be, running the algorithm forever. And so, the miracle of the next lecture is we're going to show you how we can efficiently go to infinite dimensions. Wow! So we can run the optimal fat separator in infinite dimensions, and we can still survive. Even though we've gone to a huge dimensional space, we can still survive because the number of support vectors can be small or the margins are huge. Okay, the regularization is maximum. And the regularization saves us, okay, and allows us to go to infinite dimensions. So we get ultimate power in some sense. Okay. And so stay tuned for next lecture. With that, checking out.